In our previous session, we focused on thinking about atoms, and in particular, we looked at this idea that in order to explain the discrete energy levels that exist for electrons in atoms, we had to embrace this strange idea of wave-particle duality, that instead of always thinking of electrons as little blobs of matter, as particles, we had to accept that in some contexts, and in particular in the context of electrons inside an atom, we have to think of them as waveforms. And we thought of the idea that all we can do to describe the way an electron behaves in an atom is describe a probability distribution of where the electron is, and that probability distribution behaves like a wave. So what we're going to do in this session is to extend those ideas a little bit and use them to lead on to explore the idea of what happens when atoms come together. So you know from science you've studied before that if you have separate atoms, they will often join together to form bonds. So if we take the simplest possible case, if you have a hydrogen atom, it has just one electron, and when we solve the quantum mechanical equation, which we talked about last time, to figure out what that electron is doing in a hydrogen atom, we discovered that it actually occupies a spherical waveform, a spherical orbital, as chemists call them, which is called the 1s orbital. So a hydrogen atom looks like a nucleus in the middle, which is tiny and positively charged, and it has this spherical region of space around it, which is occupied by this electron waveform, which we call the 1s orbital. So that's one hydrogen atom. If we have another hydrogen atom over here, then obviously it looks the same. But if we bring them close enough together, then we find that eventually, of course, there'll be significant overlap between the waveforms. And when that happens, we form a structure which turns out to be more stable than having the atoms in isolation. So what happens as they come closer together is that we get something that looks kind of like that, which we call an H2 molecule. And in today's session we're just going to explore that idea of molecule formation a little bit more. So because we're going to be thinking about electrons using this wave idea, let's go back to thinking about a much simpler wave, just thinking about a one-dimensional wave moving in a specific direction like this, rather than the three-dimensional stationary wave, which is what you have in an atom. And in particular, let's think about what happens when waves meet, because that's what's going to happen in our molecule formation, and just establish the principles of that using these simple waves. So here we've got one wave travelling in this direction. Let's say that we then add to that a second wave, and this one is going to exactly mirror the first one, so it has the same wavelength, same velocity, and crucially it has what we call the same phase, meaning that where there's a peak in this wave, there's a peak in this one as well. And you can see that's repeated all the way through, so they're both moving in parallel like that. So what I want you to do now is to pause the video for a moment and draw that down, and then draw down what you think the result of those two waves being added together like that would look like. And then, having drawn that one, try doing the same thing. So again, so this was case one, which we call in phase, where peak lines up with peak, and then try the second one, which is going to look like this. Where you can see that again you've got two waves moving in the same direction, but this time where there's a peak in this one, there's a trough in this one. So these ones are called antiphase. So see if you can just draw a picture of what you think the result of that superposition of waves would be when we add them together and when you add these two together. Okay, so if you've had time to think about that, let's look at the in-phase one first of all. And basically we're just doing an addition and saying, right, that where you get a small peak being superimposed on a small peak, you're going to get a big peak. And where you get a small trough being superimposed on a small trough, you get a big trough. So the resulting wave actually just has the same phase as this one, but it's just amplified. Like that, so that's the resulting wave, so still going in the same direction, but what we call the amplitude of the wave, which is the distance from the middle to the peaks, is much bigger now than it was before. And that we call constructive interference. And you can demonstrate that with simple waves like water waves and things, for example. And then if we think about the antiphase case, again when we add them together, you can see that here we're going to have positive displacement where the wave has reached a peak, but being superimposed on negative displacement here where it's reached a trough, and they're going to cancel out. And you can see you're always going to get peak cancelling out trough, peak cancelling out trough all the way along. And the consequence is that if they're exactly in phase and have exactly the same waveform and velocity, they will cancel out completely, and you get that. So the wave cancels out altogether, and that we call destructive interference. And again, it's something that's well known with wave phenomena. An example of that is with sound waves, which are slightly different kinds of waves, but they can also interfere in the same kind of way. And that's how you do noise cancelling with sound, is to generate a waveform which is antiphase in effect to the one that that's generating the sound, and when you add them together they superpose, and the sound is largely cancelled. So the question is going to be then, can we apply these ideas to those electron waveforms, the orbitals that the electrons exist in when the atoms come close together so that the waveforms overlap? So our idea is going to be then that when we have these spherical orbitals, which are these electron waveforms, and we bring two atoms together, we're going to get a region where the waveforms overlap, and in that region of overlap we're going to get superposition in the same way we did with the simple plane waves we were looking at before. And in exactly the same way you're going to get interference in that region, so they won't just overlap and ignore each other like that. You're going to get either constructive or destructive interference. It's difficult to represent this visually because obviously the waveform itself is already three-dimensional, and so the oscillation, if you like, in the wave is in a fourth dimension, which is obviously difficult for us to visualize. But you just have to focus on the idea that in that region of overlap there is going to be constructive or destructive interference. And so it turns out that you get two possibilities. Remember, the nuclei are in the center of these atoms. So if you get constructive interference, then by analogy with the simple wave, what you expect is that in the region of overlap, you're going to get a bigger amplitude. In other words, the size of the oscillation in the wave is greater in the region of overlap than it is elsewhere. And if you remember last time, we said that when we're interpreting electron waves, it's that amplitude of the oscillation which is a measure of the probability of the electron being found at that position. So in effect, by saying that there's constructive interference in the middle there, we're saying that the electron density is not evenly spread now around the molecule, but that it's particularly high in that region in the middle. So we get now a superimposed wave which looks kind of like that, and that region in the middle is the region with the highest probability of finding the electrons, because that's where the constructive interference has built up the amplitude. On the other hand, if we get destructive interference, then we know that in that region in the middle, where the overlap occurs, we're going to wipe out the amplitude. So there will be very little probability of the electrons being found at that point. So what we get now instead is something that looks kind of like this. Where these represent the regions where there's significant probability of the electron being found, and in that region in the middle, that probability becomes very small and actually will potentially go to 0 in the middle there. So you get very low probability of finding electrons in this region. So these new waveforms that result from the superposition of the individual atomic orbitals are called molecular orbitals. Okay, so the individual waveform that the one electron had in an atom we call an atomic orbital, and these are called molecular orbitals. And in chemistry, molecular orbitals are an incredibly important idea. Most theoretical chemistry that is done today is based on the idea of electrons occupying these molecular orbitals. So let's just think then about these two orbitals a little bit more. These two molecular orbitals are conventionally labelled sigma and sigma star. It doesn't matter about the labels, but we'll just use those so we know what we're talking about. So what I want you to do is pause again for a moment now and think about what you think the relative energies of an electron, or a pair of electrons I guess we're going to have if we had one electron in each atom. So think about what you think the relative energies of those electrons would be in a sigma orbital compared to a sigma star orbital. In other words, if you just do a little bit of role play and imagine yourself being an electron, would you rather be in this one or in this one? So just have a think about that for a few moments. Well, the answer in terms of energy is that the sigma orbital has a lower energy than the sigma star, and indeed has a lower energy than the separate atomic orbitals had. So if we do this on an energy diagram, which we've got over here, if these are the energies of the separate atomic orbitals, obviously they're the same because they're identical orbitals. When they merge together to form this molecular orbital, we find that the sigma molecular orbital has a lower energy and the sigma star has a higher energy. So, of course, the consequence of that is that the electrons, because electrons, like everything else, are fundamentally lazy, things will always go into the lowest available state of energy. So, if I take my pen here and I let go of it and I ask the question, what's it going to do? You all know that it's going to go in a particular direction. So if you just make your guess as to what it's going to do now, and unsurprisingly it fell to the floor. And in energy terms, you knew that was what was going to happen because I gave it potential energy when I lifted it up, and you knew that when I gave it the opportunity, it would move to a state of lower potential energy. And that's what things generally will do. So the electrons, in this case, will go to the state of lowest possible potential energy, and that means that they will go into the sigma molecular orbital, like that. So that's where the electrons end up, and therefore the molecule is stable because it's a lower energy state than the separate orbitals. However, the question is, why is this more stable? Which is what I asked you to think about, and so far I haven't really answered that question. I've just told you this is the lower energy one. But the question is why, and that turns out to be a surprisingly difficult question actually to answer. So the formation of this region of constructive interference then drags the pair of electrons into this sigma molecular orbital because of its lower energy. And conventionally what we call that sigma molecular orbital is a covalent bond, and this is the definition that's conventionally used in, for example, A-level chemistry of a covalent bond, that it's the attraction between a shared pair of electrons and the nuclei of two atoms. And in a sense that must be true because we know that this is a stable structure. The electrons go into this orbital because it has a lower energy, and by being there they hold the two nuclei close together, because if the nuclei moved apart, that orbital would cease to exist because you'd lose the constructive interference. However, it's this idea of the attraction between the electrons and the nucleus that's actually slightly problematic when we think about it. If you have two charges, so let's say we have a positive and a negative charge, and the distance between them is r, then classical physics tells you that the potential energy is given by minus k over r. So what that means is that if you make that distance smaller, so r becomes a smaller number, then obviously if you divide by a smaller number, the potential energy becomes more negative, so you're moving to a lower potential energy, which makes sense because there's an attractive force between the two, just like there's an attractive force between us and the ground. And we know that as we get closer to the ground, if I drop my pen, it's got higher potential energy now than when it starts to drop towards the ground. So the potential energy decreases as you move in the direction of the attractive force, and the same will be true here based on that equation. So now we can ask the question whether we can explain the stability of the covalent bond, the sigma molecular orbital here, in terms of simply the idea that constructive interference localizes the electron pair in the middle there. So if we say, right, here are our two nuclei which have positive charges, the question is it advantageous for an electron to be right in the middle there, in between the two nuclei, as opposed to being, for example, over here, closer to this one than that one? And we can examine that using this equation. So let's start with this situation. So right, there's the electron, and there are the two nuclei. And let's, just to make it easy, let's define this distance as 1 unit. And then that distance is also 1 unit because we're saying it's right in the middle there. Okay, so that's situation 1 that we're going to define. And then let's examine a different situation. Like that, where again here are your two nuclei, but now we're going to move the electron over to here so that this distance is 0.5 and this distance is therefore 1.5. So this is scenario number 2. So what I want you to do then is just to pause again for a moment and use this equation to work out what the potential energy would be in this situation and this situation, and therefore address the question of whether the destructive interference tending to localize the electrons right in the middle is advantageous in energy terms. Okay, so if you do that, you can see that in this case, the potential energy, we can just add up the potential energy that comes from attraction to this nucleus and attraction to that one. So it's equal to minus k over 1 minus k over 1. Okay, because it's 1 unit from that nucleus and it's 1 unit distance from that nucleus, which is obviously minus 2k. If we do it for this one, we get that the potential energy is equal to minus k over 0.5 minus k over 1.5, which is minus 2 2/3 k. Okay, so we get this rather interesting result, which is that actually the potential energy is lower in this situation than it is in that situation. So our very simple electrostatic model of a covalent bond, which says, oh, it's more favourable for the electrons to be right in the middle there, in between the two nuclei, and therefore that's why the sigma molecular orbital has a lower energy, that doesn't really seem to hold up when you actually look at the numbers. And it's clearly more complicated than that. And interestingly, you know, even now, it's not something that chemists and physicists tend to be all that clear about as to why covalent bonding is stable. There is at least one other aspect of it which is quite important, which has to do with wavelength. So remember that in the case of a light wave, we have this relationship between the energy of a photon and the wavelength of the light. So the longer the wavelength, the lower the energy of the photon. And then if we remember Louis de Broglie's idea, the wave-particle duality idea suggests that the same kind of relationship is going to exist for a wave defining the distribution, the probability distribution of where a particle is, that the longer the wavelength of that wave, the lower the energy will be. So if we think about that in relation to the molecular orbitals, you can see that in effect we've spread out the wave by having this constructive interference here. And that's equivalent to sort of increasing its wavelength. So by having a bigger spread of the electron waveform, we lower the energy. Whereas here, because we've actually said no, the electron can't go into there, and we've localized it actually more at this end, because this region where in the separate atomic orbitals the electrons would be able to go is now forbidden, we've actually decreased the effective wavelength, the spread of the wave function. And that is almost certainly a major part of why this has a lower energy. So it's not so much the electrostatic reason, it's the fact that the by spreading out the electrons, you lower their energies by giving them a longer wavelength. So covalent bonding is incredibly important. It's what holds molecules together. So, the world as we know it would be impossible without it. But actually, it's not a particularly easy thing to understand. So what we're going to do for the rest of this is not to probe any more deeply into the nature of the sort of effective attractive force that exists there, but simply to accept that there is such an attractive force, and just think a bit more about the potential energy. Let's just, before we get stuck into that, remind you a bit about potential energy, because that's what I'm going to get you to think about in a few minutes. So the form of potential energy that you're most familiar with almost certainly is gravitational potential energy. So I think we talked about this before. If I lift my pen up here, I'm giving it potential energy. And what it means by that is that it has the potential to now develop kinetic energy. If all I do is let go of it, it falls to the floor under the influence of the attractive force of the gravity. So it acquires kinetic energy as a result. And that's what potential energy means. So when you have an attractive force, or indeed a repulsive force, acting on something, but that thing isn't yet moving, it has the potential to move under the influence of that force, and so it has potential energy. And the higher I lift the pen up, the greater its potential energy is, because basically the longer that force will be able to act on it, and so the greater the speed it will be able to build up. That's the idea. So in our hydrogen molecule, we've got two hydrogen atoms, and what we're saying is that there is an attractive force between them, which is what we've just been talking about. The effect of overlap of these atoms when they get close is that a covalent bond develops, and even though that's slightly mysterious, we know it exists because we know that a hydrogen molecule exists. So there is an attractive force between the two hydrogen nuclei, and we know that what we end up with eventually is a hydrogen molecule, which is going to look something like this in terms of its electron distribution in that sigma orbital. So the hydrogen atoms have come closer together, but they don't ever end up in the same place. They don't fuse together and become one. So there is a most favourable distance that they end up with. So what I want you to do is to see if you can imagine what this graph would look like. So if we say that the distance between the centres, so between the nuclei of the hydrogen atoms, so this distance is r, see if you can sketch what you think a graph of potential energy against r would look like. So we'll put 0 here, that would correspond to the two nuclei being in the same place, and start out with them being far away, so at this side. So just imagine what happens if you do an experiment where you start with the two hydrogen nuclei far apart, so you're over here somewhere. What happens to the potential energy as they get closer and closer and closer until eventually you reach 0? Okay, so I'll give you a chance to think about that. So if you pause the video for a minute, see if you can come up with a sketch that you think looks plausible based on those kind of ideas, and then we'll compare that with what it actually looks like. Okay, so what I'm going to do is to draw a line up here which corresponds to the potential energy when the nuclei are very far apart. And we know that because we've seen there's an attractive force that can exist between them, that because we know that they're going to form a molecule when they come close enough, we know that at some point the potential energy is going to drop. just like the potential energy of my pen drops as it moves in the direction of the attractive force to the Earth. As these get closer, if there's an attractive force between them, the potential energy is going to drop. So your first thought might have been, okay, well maybe it goes something like this. But if you think about it, that doesn't seem very physically realistic. Because again, if you think about the gravitational attraction of this pen to the Earth, if you start a really long way off, like 1,000,000 miles away, and you say, right, well, what happens if it decreases to 500,000 miles away? The answer is, well, actually, it doesn't really make any difference, because the gravitational attraction of my pen to the Earth is completely negligible at those distances. You know, if you go up into space, that you're weightless, so the gravitational attraction to the Earth is negligible at long distances, and that means as you move closer but you're still very far away, your potential energy hardly changes, and it's only when you start to get close that you get this strong distance dependence. So rather than looking like that, it's going to look something like this, where when they're very far apart, the potential energy doesn't significantly change until they come into range. And in our case, that's going to be when there starts to be significant overlap between those wave functions, between those electron waves, because it's then when you start to get that constructive interference that the attractive force starts to develop. So rather than looking like that straight line, it's going to come down here, and then at some point it's going to start to decrease like this. Okay, and that corresponds now to the fact that once they get close enough, an attractive force develops. But it's not going to carry on like that forever, because obviously if it did, then eventually the attractive force would attract the nuclei so closely that they ended up in the same point, and you would have nuclear fusion, and we know that doesn't happen under normal circumstances. So something else must be happening, and that is that there must be a repulsive force which kicks in when they get even closer. So potential energy drops, but at some point, if they get too close, there's a repulsive force tending them to push them apart again. And again, that repulsive force is slightly mysterious, because your first thought might be, well, it's just the repulsion between the two nuclei, because obviously they're both positively charged, so as they get very close, you're going to get a repulsive interaction between them, and that's part of the story. But that doesn't actually account for what you observe experimentally, which is that this is really steep, this repulsive term. So what happens is that it comes down here, you reach a certain distance, and then it rises really steeply like that, and the potential energy goes up through the roof like this. And that's kind of hard to explain, but it has to do with the fact that trapping electrons in a small space, you pay an energy price for doing that. And that's something to do with something called the uncertainty principle, which is really important in quantum mechanics, but we haven't got time to get into that now. But that's why this is such a steep term here. But leaving that to one side, you hopefully realise there must be a repulsive force of some kind, because otherwise this potential energy would keep on decreasing till you reach zero, and the nuclei would all be in the same place. So if you've got anything that looks vaguely like that, that's brilliant, because that means that you've understood the issue. Okay, so when the nuclei are very far apart, they don't know about each other. So moving them a bit closer doesn't make any difference to their potential energy, because there's essentially no significant force acting on them. But as they get closer and closer, eventually those two electron wave functions start to overlap, and then you get this attractive force kicking in. So that drops the potential energy until you reach a point where that's balanced by this repulsive force, which happens at short range. And then as you get closer, you're fighting this repulsive force, so the potential energy zooms up through the roof. So that's the classic potential energy curve for two atoms. Okay, so now what I want you to do is to think about something else based on this curve. So suppose we take a pair of hydrogen atoms and we bring them to this distance. Okay, so that they have that much potential energy, because that's the distance that we prepare the system at. And then we just leave them to their own devices. So see if you can work out how that system is going to behave. So we've just got a pair of hydrogen atoms, that's R, so that's the distance between them. So there's a significant force acting on them, because you can see their potential energy has decreased relative to what it was at very long distances. And if we just now let that system evolve and do its own thing from there, just see if you can picture what's going to happen as time goes by. Okay, so I'll just leave you, again, if you want to pause the video for a second, see if you can picture what will happen. Okay, so remember, the analogy with the pen all the time is useful, that this is a state of high potential energy. As you go down towards the ground, that's a state of lower potential energy. And you know that the pen will move spontaneously in the direction of lower potential energy. That's what's therefore going to happen here. So if it starts at this point, it's going to move down the curve here, which means the two atoms are going to get closer until they reach the bottom of the curve there. Okay, so now let's pause again, and then, in case you didn't think past that point before, what's going to happen after that? Okay, so pause again, think they're going to move to this point because there's this attractive force dragging them down to there. What are they going to do when they reach that point? Okay, so if you thought about that, you can see the issue is that as it moves to a state of lower potential energy, remember, total energy must be conserved. So all that potential energy it had here, which has now disappeared, will have been converted into kinetic energy. So the more it goes down here, the faster it will be going. And when it reaches that point, it's not just going to suddenly stop, because it's got all this kinetic energy and it's got no obvious way to lose it at that point. So it will keep going in the same direction because it's got momentum. The two atoms are moving this way, they've got momentum, and they're not going to suddenly stop. So they're going to keep going up here. In other words, they're going to get closer and closer until you reach the same amount of potential energy that you started with. And at that point, all of the kinetic energy they've built up at this point will have been converted back into potential energy. And so they'll stop moving. But of course they won't stay there, because again, there's a route for them to go back down. So they'll come back down here to there and back up, and they're going to oscillate to and fro. And that's what a vibration is in a molecule. Okay, so when we talk about molecules vibrating, we mean that the two atoms on the end of the bond move to and fro relative to each other like this, and the size of that vibration is basically defined by how much energy they have, and therefore how far they can go up the potential curve on either side before they have to collapse back down. And it turns out that just like electron energies have only specific energies allowed when you get down to the molecular level, the same is true for vibrational energies. So it turns out we can't just randomly choose an energy like that, but that might be an allowed energy level, but you might then find that, you know, these are the only possible allowed energy levels in the system, and so on as we go upwards. So you get quantized vibrational energy levels, just like you get quantized electron energy levels. But this picture of what vibration is quite a nice thing to have in relation to our potential energy curve. So now, next thing to think about is what's going to happen if we start at a different point. So if we start here, whoops, that pen doesn't work. If we start here, So again, just by analogy with what we were just talking about, how's that system going to evolve in time? Okay, so have a think about that one for a moment. Okay, so you can see same thing's going to happen to start with. It's got a route to decreasing potential energy there, so the atoms will move further apart till they reach the bottom there. But then again, they're going to keep moving because they've got lots of kinetic energy at this point, so they're going to keep moving up here, slowing down as they do so, losing kinetic energy as it gets turned back into potential energy, but they can keep going until they get all the way back up to here. But you can see at this point they've got if they had enough energy to reach that point, they don't need to lose any more energy now because the potential energy doesn't get any higher, so they're going to keep on going. And so what's going to happen is, if you start from there or anywhere higher up here, once it gets back up to there, it's not going to come back down again. And what that means is that these two atoms, which started close together, are going to have moved apart, and they're just going to keep on moving. So basically, the molecule's going to fall apart. And what that tells us is that if you put enough energy into a bond, instead of just maybe moving to a higher vibrational level, it can move to such a high level that the bond will fly apart. And that's what happens when you reach a certain limit, which we call the dissociation limit of the bond. So what we're going to do now is to think about a chemical implication of that idea, that we can pump energy in to such an extent that we can actually dissociate a bond. Okay, so what we're going to have a look at is a chemical reaction, which is this: that hydrogen gas, so H2, which is what we've just been talking about here, making a sort of potential energy diagram for, can react with chlorine to form HCl. Now if you make a mixture of hydrogen and chlorine just at room temperature, nothing happens. And the reason nothing happens is that in order for that reaction to happen, you have to break an existing bond to kind of get things kick-started before the reaction can take place. So what actually happens is, because the HH bond is stronger than the Cl-Cl bond, what generally happens first is that Cl2, which is that, two chlorine atoms bonded together, breaks down to give you two chlorine atoms. And it's only once you've made chlorine atoms that a chlorine atom can react with H2 to make HCl plus H, and then the H can react with more Cl2 to give you HCl plus Cl, and you can see that that Cl can then feed back into this reaction to produce more HCl and H, which feeds back into this reaction. So once you've kick-started it by doing this, so this we call the initiation, once you've managed to achieve that, this happens very quickly in a chain reaction, because each of these steps produces an atom which can then react in the next step, and that produces an atom which can react in here, and so on. So in order to make this reaction happen, this is what we have to achieve. We could do it by breaking open hydrogen, but that's harder because the bond energy, the strength of that bond is greater. So this is what we're going to aim to do. So I'm going to give you some numbers. If we measure the strength of a Cl-Cl bond, what we're effectively measuring is the energy difference between the lowest vibrational energy state, which interestingly isn't at the bottom of the molecule, of the curve. It's actually impossible for the molecule to get to the bottom of the curve, so that's its lowest energy vibrational state. And that gap up to there is called the dissociation energy. Okay, so that's the amount of energy you have to put in to break open a chlorine molecule. Now, if you do chemistry, you're used to the idea that chemists usually don't think about individual molecules. They think about a whole bunch of molecules called a mole of molecules. So if I give you the value of that, that's equal to 240 kilojoules per mole. And if you don't do chemistry, moles will be mysterious perhaps. So I'll just tell you that 1 mole is equal to 6.02 times 10 to the 23 molecules. So in other words, to break that bond in each molecule in 6.02 times 10 to the 23 molecules requires 240 kilojoules of energy. So from that number you can work out how much energy is required in each individual molecule. And what we're going to look at is, can we provide that energy in the form of a photon? So can we put 1 photon of light in to deliver enough energy to take us up to that dissociation limit and blow the chlorine molecule apart? And it has to be a single photon, because the chances of, because the molecule, if you excite it to an intermediate stage, it will very rapidly collapse back down again to the beginning. It's like if I throw the pen up in the air, it rapidly falls back down again. So the chance of being able to have a photon to take you up to there and then another one up to the top is actually really so small as to be vanishing. So it's basically got to deliver the energy all in one go in the form of a single photon. And what we're going to do is say, well, what sort of photons would be able to do that? So in order to do that, you need to remember this relationship, that the energy of a photon is given by hc over lambda. So h is Planck's constant, so that's just a fundamental physical constant, and c is the speed of light, which is another fundamental physical constant. So if I give you the value of those, so h is equal to 6.626 times 10 to the minus 34 joules, what's the unit? Seconds. And c is equal to 3.00 times 10 to the 8 meters per second. So the question that you've got to work out is, what is the minimum wavelength, which is lambda, of photon that can cause dissociation? Okay, so take a minute, see if you can work that out using these numbers. Work out how much energy has to be delivered by a single photon to break apart a single molecule like that using these equations. Okay, so let's then see if you've got the right number for that. So we've got that 6.02 times 10 to the 23 molecules requires 240 kilojoules. So the energy per molecule that's needed is equal to 240 kilojoules divided by 6.02 times 10 to the 23. And so if you work that, you get 3.987 times 10 to the minus 22 kilojoules for each individual molecule. Now, I gave the number in kilojoules because that's what chemists normally work with, but obviously we're using base units here, so we're using joules in H, for example, and so we need to convert that to joules before we can go any further. And there are 1,000 joules in a kilojoule, so there will be 1,000 times as many joules as that. So if we multiply by 1,000, we get 3.987 times 10 to the minus 19 joules, so that's just 1,000 times this number. Okay, so that's the amount of energy needed by one molecule for it to be able to dissociate. And what we're saying is that because that has to be delivered by a single photon, we need to have a photon which has at least that much energy. So if we take this equation and rearrange it, we can get that lambda is equal to hc over E. So if E is the minimum amount of energy, then lambda will be the maximum wavelength. Because you can see that if we have a bigger amount of energy, which obviously would still be enough, if we have more energy, that's fine, that will still blow it apart, but if we have a bigger amount of energy, that will correspond to a shorter wavelength. So what we're talking about here is what's the maximum wavelength that would work. So we can just put the numbers in. So we'll say, right, that's equal to 6.626 times 10 to the minus 34 times 3.00 times 10 to the 8 divided by this number that we've just worked out, 3.987 times 10 to the minus 19. And if you work that out, you get 4.99 times 10 to the minus 7 meters. Okay, so we can calculate that if the wavelength is that or less, then a photon delivered at that wavelength should be able to blow the molecule apart, but if the wavelength is longer, then it won't. Now, people working with light in this kind of wavelength region tend to work in nanometers, which is 10 to the minus 9 meters. So 4.99 times 10 to the minus 7 is 499 times 10 to the minus 9 meters, which is 499 nanometers. So we're going to predict that if we shine light with a longer wavelength than that, it shouldn't be able to trigger the reaction, but if we shine light with a shorter wavelength than that, then it should. So we can investigate that by making a sample containing hydrogen and chlorine and shining light with different colours on it. And conveniently we have two lasers available. So we have one with a wavelength of 405 nanometers, which is in the violet region of the spectrum, and we have one with a wavelength of about 650 nanometers, which is in the red end of the spectrum. So we can compare those two lasers for their ability to trigger the reaction by noting that this one is shorter than 499 nanometers, so it suggests it should be able to trigger the reaction, whereas 650 is longer, so it shouldn't. So let's see what happens when we do the experiment. So in the tube here, I've made a 50-50 mixture of hydrogen and chlorine. And what we're going to do now is basically put our money where our collective mouth was. So I'm going to clamp this up here. And as we expected, nothing's happening because this is in a relatively low level of light at the moment. So there's not enough energy getting in to trigger any kind of reaction. So now we're going to see what happens if we apply some red light to it. So if I take this red laser, and you can see on the wall over there behind the red light from the laser there. So we're going to try shining that into the mixture and see if it has any effect. Okay, so here we go. Okay, so we're shining the red light directly into the mixture, and as you can see, nothing at all is happening. Okay, so now we're going to try the same thing, and this one is a violet laser. So if I shine this one onto the wall, you can see the violet there. Okay, so here comes the violet laser. Let's see what happens. Okay, and as you can see, it worked. So that seems like a good place to end this session. So what we've done today is to look quite deeply into the nature of chemical bonding and seen that there's a lot more to understanding what we mean by a covalent bond between atoms than simply the picture of, oh, they share electrons. That really understanding what's going on requires quite a lot of thought, using ideas from both physics and chemistry.